Hello everyone, it's been a while but we are back, we are live and it is Physics Rocks, it's true. This evening we are going to take a look at Huygens Slits, diffraction gratings and all things interference. And to start with we're going to need to learn about something called Huygens Principle. Okay, so basically the idea is this, that you can describe wave behavior as a series of wavelets that are coming from a particular spot. Okay, so what we're going to do is we're going to imagine that we have something like a little pond. Okay, so we've got a little rectangular pond. What I'm going to do is I'm going to drop a little stone into the pond at this point here. And what we'd expect to happen is that across the surface of the water we would get a series of concentric circles that will come outwards as ripples moving out in time. Okay, that's not particularly exciting or challenging, but the question is, why does that happen? And the concept that Huygens came up with was that if you consider that this circle here, this individual ripple, what he said was that any point on that circle was actually a secondary generator of wavelets, and that a wavelet generator was there was a point, and then from that point a wave came out in a circular fashion, expanded away from that point like that. Okay, and then at any given time later on, any point along that circle was also creating little wavelets. Okay, so to start with, you got a small circle that came outwards, but then a little bit later, all of these bits here, you could see if you take any circle here and you make lots and lots and lots and lots and lots of circles along the inside using the center point as that first ridge, then all the outer ridges touch that next circle. I'm going to color that one in red just so you can see it. Okay, so if all of these little points end up on this red circle at the same time, his argument was that they would interfere, they would superpose with each other, and all you would see would be this circular ring. Okay, so let's maybe take a look at that in slightly more detail at closer range. So once again, let's imagine that we have a little circle here, and we have a center point here, something's caused a disturbance, and we have a ripple pattern. Now what we want to know is, at some time later on, where's that ripple pattern going to be? Now in this case it's not particularly exciting or interesting because we know it's going to be a circle, but what we're going to do is we're going to build that. I'm going to show you how it is. So let's get a circle, let's get some red circles. Let's make that a circle. Okay, and let's put a little dot in the middle of it so we know where its center point is. And if I can get it in the middle, that will probably help. So around about there, and we're going to group those together, and then we're just going to clone these over and over again. So if I put another one there, and I put another one here, and another one here, I just move my way all the way around, just keep continually putting a little circle anywhere I like on this edge. What I'll eventually do is I'll make enough circles that actually just generate an edge out here. I'll color this in almost perfectly so that there's a little sphere or a little circle on top of that that's filled in that has an outer circumference that goes along this one. Okay, and Huygens Principle says that this is what you'll observe because all of these ones coming back inwards will cancel each other out. These ones going left and right will cancel each other out. You get interference in those. So the only one that actually survives is the one heading outwards. And that's how we get kind of outgoing wave patterns. So it goes outwards and outwards and outwards. And this is not particularly controversial. Okay, this is what you observe when you drop an object into water. Okay. The more interesting kind of end of things is that if we were to do the exact same situation, but this time maybe have multiple setups. Okay, so let's have multiple little wavelet generators here. Okay, and lots and lots and lots of them all together. Let's take a look at what happens in this case. What we're going to do here is we are just going to try a little arc. We're just going to look at what happens forwards because the side-to-side stuff gets a little bit messy. Okay, so this little wavelet will create a full circle, obviously around, but let's imagine that we're just looking forward, so it just creates this arc. So this one creates this arc. right? And the one next to it will create, it being identical, will create an identical arc. And the one next to it will create an arc. And the one next to it will create a little arc. Okay? Now, we can ignore these bits here because they're going to cancel each other out. So all of that can be ignored. And what we're left with is kind of a bump, 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 curvy thing going on here. So if I had 4 wave generators, 4 little droppers in the water, what I'd end up with at a given time here would be a wave pattern or a ripple that looks a bit like this. And if you're observing it on the pond, then what you would see is a curve at the edge, across a little dip, across a little dip, across a little dip. Okay, and this is what ripples move out like. That a little bit of time later you get this, and a little bit of time later you get this, and this is ripples if you dropped something like a stick into the water. Okay, so that's the type of ripple that you would get if you dropped a straight object in. You get a ripple that looks a bit like this. But the reason that you get a ripple that looks a bit like this is that every single point along the edge here is considered to be an individual little creator of wavelet patterns, all of which are little circles or little arcs that add together to give you this straight line pattern. Okay. And this is why the phenomenon of diffraction occurs, because if I have a barrier of some description in my water, and we are just talking about water, we will get on to light in a moment, but we talk about water to start with because it's a little bit more intuitive. So let's imagine that I have some perfectly straight waterways. I mean, I've done a really good business of drawing them on. So I've got some waterways coming into here, coming into here, and coming into here. Now the reason I'm getting perfectly straight waterways is because I have all of these tiny, tiny, tiny little Huygens Principle arcs. So let's draw a few in here. So let's get a little dot there with a little arc over the top of it. It's not great, but it'll have to do. And then let's clone them out a bit. So put one there. One like this, and one like this, and then copy that whole lot down there. Copy and paste. How lovely. Okay, so we have this huge army of little dots that creates this wavefront. Okay, that all of these little bits and bobs add together to give what's essentially a straight wave. The issue is when you come to a barrier that an awful lot of this wave is just going to be either absorbed or reflected, and the only bit that's actually going to go through the middle is the bit that gets into this kind of region here. All right, that means in this case we're going to have much fewer little arc building systems that are available here. So when they come out on the other side, the little arcs make that, and then on top of the next bit, each of these little points becomes its own little wave generator. And they generate their own arcs. Let's give them a red. So that one generates a little arc, and that one generates a little arc, and that one generates an arc, and that one generates an arc, and that one generates an arc. And what you can see happening is that as this comes out, we lose that beautiful straight lineness, and we start to develop a curve. And this is why Huygens and Fresnel, actually, this is called the Huygens-Fresnel principle, was the idea that these little wavelets are the reason that you get diffraction systems happening. Any individual point can be considered its own individual wavelet creator, and what you see at the end is simply the result of all of those waves superposing on top of each other, adding together or subtracting from each other, where a crest meets a crest and a trough meets a trough, or a crest meets a trough, depending on what occurs. And you end up with these diffraction patterns. Now, so far that's not very interesting. It's certainly not very controversial at the time. But the argument is that this can be applied to light. If light is a wave, then it should behave like this as well. And it was certainly known that light does diffract. But the concept of light at the time was very much that light was a series of particles, or corpuscles, as Newton would have described. And the idea being that a light particle, as in a particle of light, not a particle with very little mass. So if this was a light particle here, if it came and ran into something, it simply bounced off like a ball. Okay? Hence, reflection was a thing. Bounce, bounce. If it moved from one material into another, it slowed down, and as a result of that, it changed direction, because that's what a particle would do, moving from one material to another. Diffraction of light was observed, but again, it could be explained. It could be explained using this corpuscle model, because if I had some form of screen over here, so I was observing light and I managed to make a gap small enough to make light diffract through, then what you ended up with was the light was like a smear over here, with a lot of it very bright in the middle, and then it getting less bright towards the edges. So that's, oh, I didn't mean to do that. Let's fill that in, and let's make it a nice yellow color. Okay, so it was certainly brighter in the middle, and then less bright out towards the edges. Now, this was sort of what you would expect from a diffraction pattern, but it could also be explained by if you had a particle comes through, this particle comes through, hits the wall, no problem at all, it becomes part of that. Then another one comes through at a bit of an angle, but there's less of them, that hits down there. And then maybe the other one comes through, bounces up, comes up there, and then something comes up here and bounces up and hits up here, and you get this kind of weird spreading of the light, where you would expect to see a pretty heavy spotlight, you get a smearing of light because the gap is so small. That seemed reasonable. That seemed completely fine. The issue was that in 1802, a scientist called Thomas Young came along, and he did something rather interesting, which was that he got a system set up where you had a gap here, which is not particularly interesting, but he had another gap up here. And he shone monochromatic, coherent light. That's light of the same frequency, the same wavelength, and the same phase at this. Now, how he achieved that was he had a bulb here that was producing monochromatic light, and then he put that through a single slit, so that the light would then be diffracted out into both slits. Now, that didn't matter whichever way you wanted to think about it, whether you thought about it as a wave or you thought about it as a particle, it didn't really matter at this stage. It was a particle. Some bounced and went through there and would hit up the screen, some bounced and would hit through there and go up, and so forth, just kind of like that. Or if it was a wave, you'd get diffraction over through this area. Draw that in quickly. You'd get the wave would diffract out, and then when it strikes here, you'd get little wavelet creators in here that would create further diffractions. Okay? One or two things would be going on. Okay. Now, if it was this type of pattern, what you'd get is you'd be expecting the kind of same smeary effect. Some of it would go straight through. Oh, pardon me. Some of the light would go straight through. Some would be up there, but you just get this broad smear of light. That's what you expect, and that's not what Young got at all. Okay, what Young got instead was a pattern that looked a bit like this. Okay, that you had a certainly very bright central fringe, exactly what you would expect from light going straight through, but then there was areas of darkness, followed by areas of brightness, followed by areas of darkness, followed by areas of brightness. Now, this is an interesting phenomenon because this is interference. Okay, this is where you get bright areas where two bits of light have arrived together in phase with each other, and they've constructively interfered with each other to become brighter. And then where a crest has met a trough consistently at a particular spot, you get completely destructive interference, and as a result, you get darkness occurring here. So you get a complete lack of light. Now, this really threw the corpuscle particle idea of light out the window, because imagine throwing two tennis balls that struck a wall at exactly the same point at exactly the same time, and that they simply cease to exist. That's not what particles do. They would bounce off, they'd hit the wall, they'd hit the wall, double in effect. You would have expected this to be probably centrally bright and then gradually getting dimmer towards the edges, and that's certainly not what's happening here. It's bright, dark, bright, dark, bright, dark, bright, dark. And this led Young to believe that what we had instead was a situation where, in fact, it was waves. It was waves going on here, and the general setup looks a little bit like this. Okay, that you have a monochromatic light source of some description that's producing light in nice and a consistent wavefronts. It strikes a slit. The slit width usually less than a millimeter. That will create some nice diffraction here. Those diffractions will then go on and create and go into these double slits. Okay, these narrow slits here, and they will then diffract out as well. Okay, creating more diffraction. Now, what you should see is that there's an area here where those two sets of waves are overlapping with each other. Okay, that part of the wavelet on this end is overlapping with this wavelet here. And because these two are interacting now with each other, we're going to see these two things interact. We're going to see superposition and we're going to see interference. Okay, so it's in this area here on the screen that we get our interference pattern formed. Okay, so on here you get that picture there. You get this setup here. You get bright, dark, bright, dark, bright, dark, bright, dark, bright, dark. Okay, now if you considered that you had the screen over here and you had your slits over here, then this distance here would be called D, the distance from the screen to the slit. Okay, if you have two slits, then the center of one slit to the center of the next slit, I'm going to do that a different color so that you can see it a bit better. So from the center of this slit to the center of that slit, we call that the slit separation or the slit spacing, and that is given the letter A. Okay, on the screen I'm going to grab my little picture here. So on our screen here we get this image. So that becomes this. Here we see this on the screen. The distance that there is between any two fringes, so between the center one and the one next to it, or between between the center one and the one next to it, or between this one and this one, or between any two fringes. We call these bright spots and dark spots, we call these fringes. Any of these two that are sat next to each other, we give these the letter Y. Y for reasons. Okay, now with some severely interesting trigonometry that's slightly beyond the course of this, the scope of this course, you can show that the wavelength of the light that you're using is equal to the slit spacing A multiplied by the fringe spacing Y divided by the distance from the screen to the slit. Now, I'm not going to show you how that works in terms of trigonometry. I would love to, but we've got a lot to do in this stream. If you'd like to see how that all works out, it is just lots of Pythagoras theorem. Put a little comment below. I'll do an explanation video. If that's something that you'd like to see, is where does this equation come from? Okay, but this is the Young double slit equation. That the wavelength that you're using, because remember we're using monochromatic light, so that is light of a single wavelength, so lambda has a singular value, is equal to the spacing of the two slits apart multiplied by the spacing of the fringes. Now notice the slit width doesn't matter, it's the spacing between the slits that matters. Okay, so it's AY over D. All we have to do is have the slits here narrow enough to actually generate diffraction. Yeah, after that, it doesn't matter, really, in terms of this. And we can use this because we can measure the distance between these two slits in the lab. We can measure the distance Y with a ruler on a screen, and we can measure the distance D, which allows us to get an accurate and sensible value for the wavelength of the light source here. And that's important because once you can get the wavelength of things, you've got their color correctly. And if you're looking at it in chemistry and you're doing flame tests, you're doing all sorts of things like that, then you can determine, well, if that's the wavelength of light that's being absorbed in an emission spectra or an absorption spectra, then you can actually work out what elements are present in this thing. So the ability to accurately calculate the wavelength of light that's coming from a particular source using simple lab measurements is actually super, super useful. Okay, so this is the Young equation, or the Young double slit equation, and it's good. There's nothing wrong with that at all. Okay, but can we do better? Could we do better? Because in theory, we should be able to perhaps add a third slit up here. Okay, and assuming that our light reaches up here, it will create another set of diffractions, which will give us more interference. But in an interesting way, that it will actually generate more profound bright spots, but actually generate more dark areas. So it will actually separate the fringes out a little bit more. Okay, and if we added more and more and more and more and more slits, we could perhaps get a situation where we would get better and better and better information about lambda. And that's what this is all about. This is about, can we get the best value of lambda here that we possibly can. Okay, so what we're going to do now is, having established Young slits here and its equation, and it works and we can get it and it's not a problem at all, and let's just, before we go on any further, let's remember that we define some terms here, that A is the slit separation, and that Y is the distance between adjacent fringes. That's off the end of the screen, so let's bring that up. And that D is the distance from slits to screen. Okay, and ideally you'll have these all, well, not ideally, you will have these all measured in meters, because you'll have meters times meters, which is meters squared, divided by meters, which is meters, and you get your lambda in meters. Okay, you can do it in millimeters, provided you're consistent on your measurements here. You should be absolutely fine. You'll not run into any trouble that way at all. Okay, now onward then, onward. Let's move on to, well, what happens when we add more and more and more and more and more slits. Well, what happens is you get less and less and less bright spots, but they get much, much, much easier to pinpoint, because the real problem here is measuring this distance Y, because on a screen these might be a few millimeters apart. Okay, and that introduces a pretty hefty level of error into your calculation. And if we're trying to get as accurate a value of lambda as we possibly can, our primary source of error here is this distance between adjacent fringes. Okay, this pattern is, well, it looks pretty big on screen, depending on the size of your screen, I suppose. If you're looking at this on a mobile phone, then you're probably around about the right scale for having to measure these distances, and that's too small for us to be comfortable with in terms of getting ourselves a really, really, really good value. Okay, so what I'm going to do is I'm going to try and move these fringes a little bit further apart, make them a little bit more defined by introducing more and more diffractions that are going to do more and more interference. All right, so we had 2 slits, so the logical step would then maybe go to 3 and then to 4 and then to 5. Now I'm going to skip the 3, 4, 5, and I'm going to go to around about 600 per millimeter on a particular little piece of material. So let's imagine that I have a piece of material here, and what I've done is I've got this as completely opaque, but I've scored lines on it with an unbelievably thin pencil, up, down, up, down, up, down, up, down, so that they're all parallel to each other, uppy, downy, like this, and my ability to get these the right distance apart is going to be tested severely here. And if you're super into things being lined up, I apologize for the major triggering I'm doing on you right now, but we'll be alright. It'll be fine. Can't even click that one, it's out of place. That's annoying. And let's get this last one in place. Spent too long drawing things. Okay, so if I had a setup like this, where I had hundreds and hundreds and hundreds and hundreds of little lines across a particular piece of material, then I would call this material a diffraction grating. Okay, because it's like a storm drain outside the house. If you have one outside your house on the road, they're in the road and the water runs kind of down the street and drops into them. Okay, it's a grate. So this is a diffraction grating. And what we're going to do is we're going to shine our ray of light at it. Now bearing in mind that this is extremely small, so our ray of light is going to hit like this. Okay, so let's imagine it's a red ray of light. So boom, like that. It's going to come through each of those little gratings, and at each little one, because each of them is a very thin slit, it's going to be diffracted outwards. So we're going to get hundreds upon hundreds upon hundreds of diffractions. And that's going to be quite a challenging diagram to draw. So let's just look at 3, and I've pre-drawn it because we could be here all day. So let's have a look at this. All right. So if I have my rays of light that are coming towards them, let's imagine them now as nice, plain, flat wavefronts coming in, like this. So they're incident, monochromatic wavefronts. Are we okay with that? Incident meaning they're what's coming in, monochromatic meaning they're of a single wavelength and frequency, and wavefronts basically means that they are the additions altogether already done of the bits of the Huygens wavelets. So we've got just the result of this. Okay, as they hit each of these little thin slits, their little Huygens wavelets become apparent to each other. Okay, now you would think then that what you're going to get is that these wavelets will go out, they'll all hit this screen, and you'll get this massive interference pattern. But in fact, you won't. Okay, because if we just follow, I'm going to make this slightly bigger because I want to follow this guy. Scale this up a bit. Let's imagine I follow this path here. So I've got just randomly along here. Let's go to this point here. Okay. It is highly unlikely that when this crest arrives, okay, when it gets here and it copies its way all the way around, at the instant a crest arrives here, it is profoundly unlikely that it's going to meet a crest from this one. And if it does, it's even more unlikely that it's also going to meet a crest from this one. And that's just 3. If you have another one up here, and another one up here, and maybe 600 per millimeter, the likelihood of you meeting crest after crest after crest after crest after crest is extremely small. Okay. In fact, if you have lots and lots and lots of them, then basically what you're doing is you're playing addition with random numbers. Now, if I ask you to pick 600 numbers, but I'm going to limit you. Let's say your numbers can range from -10 all the way up to +10. Okay, pick a number between -10 and +10. All right, you got it in your head? Excellent, right, cool. Now, pick another number between -10 and +10. All right, add them. So, for example, if you had guessed 6 to start with, and then -5 afterwards, when you add them together, you've got 1. Okay, so 6 plus -5 is 1. So that's what's happening here, that a random amplitude of, say, 6 arrives with another random amplitude that's maybe -5 because it's coming towards a trough, and you're getting an overall interference of 1, that you get an amplitude of 1 on the board. Now, let's play this game randomly. If you chose 600 numbers randomly between -10 and +10 and then add them all together, the most likely result that you're going to come up with is 0. Okay, and certainly 0 plus or minus 10 or plus or minus, say, 5 is extremely likely. You're going to be somewhere in that region, and the more and more times you play this game, the more lines you have per millimeter, the better this game gets. Okay, this is just simply random statistics. So in most places, what you're going to get is at any given point, the overall amplitude at that point is 0. However, there are going to be very, 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 very peculiar little points like this, where it does actually work, that you do get wavefronts that are formed and travel towards it. And I've tried to draw it on this diagram as well as I can, but let's have a look. If I have the crest of this wave, right, at any given angle, if I have a wave front that goes that way, notice that the crest of this wave does not meet the crest of this wave. So if I continue that wave front onwards, when it strikes the screen, you're going to get nothing. Okay, but if I slightly bring this round and try this wave front, then the crest of this little wavelet and the crest of this wavelet actually meet each other, don't they? Now, they're not the same wavelet. Like that one should be matched with this one perfectly. Okay, and we could do that. We could just go straight across. Right? Yeah, that works. Okay, crest meets crest meets crest. Happy days. Okay, so if I go straight across, boom, I should get a perfectly nice bright spot. If I go, however, along this line, I will also get a bright spot if I manage to get it out a little bit further with this. Because here, my crest meets this crest, and as I come along and introduce new wavelets into it, this crest meets this crest meets this crest, if I could line it up properly. That's better. And we have another set of crest added to this situation. And as we go on, the crests that appear, or the wavelets that appear further down and the wavelets that appear further up, at all times we're cutting across their crests. So they keep reinforcing each other until they arrive at this point on the screen. And because they all arrive together, and they all arrive in phase, and they all arrive with amplitudes, crests meet crests, trough meets trough, and you get a bright spot formed on the screen. Now this bright spot is in a very small place. It's a very, very, very defined spot on the screen. Okay, but it's there, and it's useful because everywhere else is darkness. And we can use a little bit of trigonometry, and we can work out exactly what the wavelength of these things has to be from measuring some distances. Okay, so let's zoom in a bit. Okay, let's just take a look at what's going on between these two slits and see if we can get some form of mathematical relationship going on here. So let's take a look at this in slightly closer detail. So all I'm looking at now is these two slits. Okay, so these two slits a little bit higher up. Okay, so let's have a look at them. Okay, so this is my top slit and this is my bottom slit. I've taken out the wavelets, but they would still be there. So wavelet here, come out like that, and then a little wavelet here, come out like that, and they're overlapping. Okay, but they're overlapping to form this wavefront here. Okay, now let's take a look at some distances and some setups here. So let's say that the distance between any two given slits here, let's call this distance d. Not to be confused with the distance d from the young slit, which was the distance to the screen. This is simply the separation between any two adjacent slits. Okay, this is d. Have enough of that. Now, if we consider that the original waves were traveling this way, and that we are now getting a wave that's being deflected down this way. Okay, we're going to call this angle of deflection theta. All right, so that's theta. And just by a bit of similar triangle stuff, that's theta. Agreed? Hope so. Which means that this angle in here, because this is a right angle, this angle is 90 minus theta, because that is a right angle, because that's the direction of travel, which is at right angles to the wavefront itself, which makes this angle in here theta. And this is what we care about, so let's text that. So what we've got here is we've got the separation d, we've got the angle of deviation as theta. So we'll put that in there, angle of deviation. Let's put it in English, that would be actually quite helpful. It's the angle of deviation. All right? And these are all theta, so that's theta there, that's theta in here. Now, this gap here then has to be, logically speaking, the wavelength. Agreed? Because there's a wave and there's the next wave. So it's the wavelength, lambda. Now, let's imagine that when we don't have all the information, we're actually going to say that this is n lambda, where n is some integer, because it could be that we missed out one of the potential ones in between. So we're seeing this wavefront and we're measuring this wavefront, but maybe there's a wavefront in between. Okay, but what we do know is that this is some number of wavelengths, this distance here. Okay, which is the distance between a crest on one of my wavelets and some future crest on one of my other wavelets. So in my little diagram here, it's the distance, say, between this crest and maybe this one out here. Yeah? Okay, so that'll be 4 lambda as opposed to just lambda. So this is some n lambda. Okay, now what we've got here is we've got a right angle triangle, because that's a right angle. That's D, and we're going to move that in here to form the hypotenuse of my right angle triangle. So let's draw that over to the side, because that can sometimes get a little bit confusing. So I've got a line there, that's of length D, a line here, that's of length n lambda, and a line here that connects them up, that we have absolutely no idea what it is. That's a right angle, believe it or not. And we have that this is n lambda, this is D, and super importantly, the angle between these is theta. Okay? And now we have opposite over hypotenuse. And we can write that sine theta is equal to the opposite, which is n lambda, divided by separation between the two slits, which is D. Okay, so sine theta is equal to n lambda divided by D. Right, so we're getting there, because if we could measure theta somehow, and we knew what n was, then we could measure certainly D, then we could probably find lambda in there, because we've now got an expression for n lambda. Now we're going to write that as that we're going to multiply both sides by D to get D sine theta is equal to n lambda. Okay, and this is called the diffraction grating equation. That d sine theta equals n lambda, or probably more commonly the other way around, that n lambda is equal to d sine theta. Okay, so how do we go about getting these values? Like, this is great, wonderful, wonderful, wonderful. We could probably rearrange this for lambda, but I've no idea how to get n. Absolutely no idea whatsoever how to measure d, and sine theta is just some randomness. Okay, so but we can measure all these things. We can measure them all from the results of this experiment, which I haven't actually shown you yet. Okay, so if I take this experiment and actually do this experiment, then let's turn it into this. So I have my diffraction gradient here, and I have a screen over here, and I have some form of monochromatic light. Usually it's laser light at this stage, for lab purposes. But anyway, any type of light will do nicely. Then what you get is you get a bright spot directly across. Because remember I said the straight up and down one actually works. Okay, so straight wavelets will go through, and we get a very bright spot formed here. Okay, you get a bright spot formed there. Lovely. Right. Then what you get is a gap where there's absolutely nothing. And then there's a next bright spot over here. And then there may be a next bright spot over here somewhere. Usually these angles are a bit different. Okay, and you get the exact inverse of that as well on the other side. So you get the symmetry going on as well. Which makes sense, because if it's going to be deviated through an angle theta, well, theta can be up or theta can be downwards. It makes no difference whatsoever. Okay? Now, it turns out that your central one corresponds to a situation when n equals 0. Okay, now that makes sense because remember n lambda is equal to d sine theta. Okay, and the angle theta is the angle between this central line, mark that in as a central line, the angle between this central line and wherever your little maximum appears. So for this one out here, this angle will be theta. If we're looking at this one all the way at the bottom, then it'll be this big angle will be theta. Okay, but for the first one, theta equals 0. Yeah, because there's no angle, it's just gone straight through. And the only way that theta can be 0, which gives sine theta equals 0, which would leave me then that n lambda has to equal 0 for the middle one. So n has to equal 0. Because lambda can't. Lambda is the wavelength of the light, and it's not 0 because the light exists. Okay, so this we call the n equals 0 position. Now, the next position outwards where we see a maximum is when n equals 1. Why is that? Because if n didn't equal 1, then this distance n lambda wouldn't be a whole wavelength, and if it wasn't a whole wavelength, then we wouldn't be seeing a bright fringe. If this has to be 1 because there's no maximum closer. The closest maximum has to be n equals 1, and then the next one out would be n equals 2. Okay? Hopefully that makes sense. And this is the first maximum, and this is the second maximum. So what about these ones up here? Well, they're also n equals 1 and n equals 2, because their value of theta is exactly the same, it's just in the opposite direction. So if I was to calculate n lambda equals d sine theta, then I'd have to get, if I got an angle, say, of 12 degrees, then 12 degrees could be that, or it could be that. So these are both n1. And are we following along? I hope we are. I hope we are. Right, so n lambda equals d sine theta is the equation that's going to govern all of this. So we've got our n1, n2 positions, and we might even get n3 and n4, and we'll talk about that a little bit later. But here we go. What we've got is we've got a central maximum, and we've got this. Now I can find theta from here now. I can find theta by doing some very, very, very straightforward in-lab measurements, because this is the angle theta. Then all I need to do is measure the distance from the screen to my diffraction grating. We'll call that x. Okay, the x distance here. And then all I'll have to do is measure the distance from the central maximum down to my first maximum. Okay, so from my n equals 1 point to my n equals 2 point. Let's call that y. Okay, because if I take x and I take y and I can put them together, I will once again form myself a beautiful right angled triangle with theta in it. And this time we have an opposite over an adjacent. So we can write that tan theta is equal to x over y. Okay, where x is the distance from grating to screen, not up here, and y is the distance from the central maximum to your nth maximum, depending on what you're doing. Because this will work for any of them. Okay, because all I have to do is just, if I change that, x stays the same the whole time, it's just the screen distance. But y is simply moving here. And we can use the tan theta equals x over y, and therefore by trig or by inverse functions we can write that theta equals the inverse tan negative 1 of x over y. And that will allow us a value of theta. Brilliant. So we have, we'll get a value of theta ticked. We've got a value of n just by counting it on the board. So all we need is a value of d. D is straightforward because we've built our diffraction gradient to have a certain number of lines per millimeter. Right, so there's 600 lines per millimeter. Then the separation between the two, let's just do that, 600 per millimeter, then there are 600 lines per 1 millimeter. Okay, then we simply take this the other way up. Then we have to have 1 over 600 millimeters per line. Okay, which is 1 over 600 times 10 to the negative 3 meters. Okay, we'll just pop that into our calculator and have that ready for it. And that's our value of D sorted out. Okay, and most manufacturers of diffraction gradients will actually give you the distance between them, so that's fine. So we have n, we have d, we have theta, we have everything we need to find lambda. Okay, so let's do an example. Let's do an example, and that'll finish us off. Okay, so let's imagine that we have a diffraction gradient. I'm doing this off the top of my head, so apologies for the bad typing. I've also got a new keyboard if you can hear the clickety clacking. So we have a diffraction gradient with 500 lines per millimeter that forms a set of maxima on a screen that is placed 1.5 meters away. The distance between n equals 0 and n equals 1 maxima is, let's say, 34 centimeters. Okay, and this could come out really badly, but let's see how we get on. Okay, find the wavelength of the light. Okay, so first things first, let's get a diagram done up of our setup. So we've got our diffraction gradient here, we've got our screen over here, we've got our central point maximum here, boom, pop it in, and then we've got our n equals 1. Oh, we'll exaggerate this a bit with n equals 1 on both sides there. Okay, so we know that this distance here from the center of my gradient to my central maximum, my screen distance, even that up a bit, we know that that distance is 1.5 meters. Okay, and we now know that the distance from the central maximum to here is 34 centimeters. And I'm not going to fall for, or I'm not even going to be tempted to fall for a unit conversion problem. So we're going to go with everything in meters just to be safe. And that's my ray, and I'm looking for my angle theta. Here, so theta will be in here. Okay, so what do we know? We know that the equation we want to use is n lambda is equal to d sine theta. We know that. We want to use that. We also know that this is the n value is 1. Okay, because it's the distance between n equals 0 and n equals 1, so we're looking at the n equals 1 situation here. All right, we have an idea what d might be because we've been given the number of lines per millimeter. So let's get that right. So d equals 1 over 500 times 10 to the negative 3 meters. I don't like leaving it like that, so I'm going to go and grab my calculator and do 1 divided by 500 and that, which gets me 2 by 10 to the negative 3. I'm going to multiply that by 10 to the negative 3 to give me 2 times 10 to the negative 6 meters. Okay, so the separation between one slit and the next slit on this diffraction gradient is 2 by 10 to the negative 6 meters. Okay, so we've got n in the bag, we've got d sorted out. All we need to do is get theta sorted out, and we've got we'll have a good setup for lambda. Okay, so finding theta is straightforward enough because we'll just use the tan theta is equal to the opposite, 0.34, divided by the adjacent, which is 1.5. Rearrange that then to give me that theta is equal to the inverse tan of 0.34 over 1.5. Calculator's on standby on this one, so we're going to do 0.34 divided by 1.5 equals, that's 17 over 75, or 0.226 recurring, for those of you who are big fans of the intermediate steps. That gives me that theta equals, quite pleasingly for numbers off the top of your head, 12.77 degrees. If the angle theta is 12.77 degrees. Cracking. Okay, so we now have theta. Here we go. So now what we want to know is what's the wavelength of light that's illuminated this. A quick rearrangement of this will give me that lambda is equal to d sine theta over n. And since n equals 1, lambda is simply d sine theta. So lambda is equal to d, which is 2 times 10 to the negative 6, sine theta, which is sine 12.77. I'll bring this little text box up a bit because I want this to be nice and central. Gives me that lambda is equal to, calculators on standby, that's 2 by 10 to the negative 6, multiplied by the sine of 12.77, which gives me 4.42 times 10. Oh, I'm in symbol. Get that right. So 4.42 times 10 to the power of negative 7 meters. Power meter sign. So lambda is equal to 442 nanometer light. Specifically 442 nanometer, okay, and not a bit more or a bit less. And that's the critical bit. That's the critical bit, because 442 nanometers happens to be the particular color of light that's, say, associated with, I don't know, like a strontium bulb. Then we know that strontium is present in this light. We can use that to determine what something's made from. And there's all sorts of uses for these diffraction gratings. We'll maybe go into that next time. But for now, what you need to be able to do for your exam is to be able to use n lambda equals d sine theta, be able to build this diagram with this information, and be able to calculate a value of lambda. Okay? You need to be able to explain, not necessarily do anything with it, but explain this little wavelet pattern and how it can lead to dark and bright fringes in the young double slit situation. Okay, you can also get single slit diffraction. We haven't talked about that in this one. We'll talk about that in a future video. Single slit diffraction is a little bit interesting. Double slit diffraction is a little bit easier to deal with, interestingly. Right, we need to be able to use lambda equals ay over d, where a is the slit separation, the distance between the center of one and the center of the other. Y is the distance between two adjacent slits. Okay, watch out for exam questions that give you maybe this distance here. Okay, and then it'd be, you measure this distance, that'd be 1, 2, 3, that'd be 4y as opposed to y itself. Okay, so watch out for that. And d is distance from the screen. Then we've got the diffraction gradient thing. Interestingly, you probably don't need to be able to explain any of this, but it's a good idea to understand where this all comes from. Okay, there's been a lot of heavy theory in there. If you'd like me to show you the Pythagoras kind of setup for how you get bright fringes and dark fringes, and you get this equation lambda equals ay over d, I'll leave me a little comment below and I'll make you a video on that one. Hopefully this has been useful to you. It's been a long time since I've been talking to most of my own students, and I'm starting to miss them. So I will leave you with just a gentle reminder that physics rocks. It's true.